Hello everybody, welcome back to our physics engine programming. We are coding a physics engine from scratch in C# using MonoGame. But we're coding this in a general way, hopefully, so you can just learn from this and apply it to whatever programming language or graphics API that you have. So if you like what we're doing with these physics videos, please like and subscribe and share. So what we're going to do today is we're actually going to completely separate the narrow phase and the broad phase. The way we're doing it right now, the broad phase is actually a little bit intertwined with the narrow phase. I'm doing a lot of collision stuff inside of the broad phase. So the purpose of the broad phase is simply to find pairs of objects that are possibly colliding, or they're close enough that they need another look. And then send that all off to the narrow phase. And the narrow phase can just do one single loop where it just loops through all the possible colliders and then finds out if they're actually colliding and then resolves those collisions. Let's take a look at the code and see what I'm talking about. All right, so here we are in the collision step. We're doing the movement step, and then right here I have this double for loop where we're looping through every body and comparing that to every other body and deciding if they're close enough that we need to actually do some collision resolution. But inside of this double for loop, I actually have a collide function. And I need to get this collide function out of there. I just want to record pairs of objects that are possibly colliding, and then inside the narrow phase, we'll use this collide function to find out if they're actually colliding. I'm also thinking that by moving this collide function outside of this double for loop, we should get a performance increase as well. So the complexity of this double for loop is about n squared over 2, or n squared divided by 2. And so the less complicated I can make this code, the faster it should run as well, is what I'm thinking. So I'm going to put this code in release mode, and let's just do a test and see what we're currently getting. In fact, I'm going to go back to the game class, and I'm going to get rid of the ledges that we have in there just so I can put more bodies on the screen. I'm going to put about 100 bodies on there, and let's just see what kind of performance we're getting currently. All right, so I got rid of the ledge, and so we're just going to have the ground body on the bottom. Let's go ahead and run this and see what it looks like. All right, and I'm just going to throw a bunch of box bodies in here. At 100, we have 100 bodies in here, and the step time is taking about 2.5 milliseconds. And actually, before we move on, we're still recording the contact points, and I think I want to get rid of that. We've already tested the contact points list, and I'm satisfied with the way the contact points are being calculated. So I'm going to get rid of the contact points, and then let's do this again, and we'll get a baseline for our performance. Back in the flat world, let's go ahead and get rid of the contact points display list. So here's our contact points. I'm just going to get rid of all of these. In fact, let's just comment them out just in case we want to bring them in later. But we're not going to record the contact points at this time. Okay, then right here, I'm going to get rid of this as well. Back at our game class, where we actually display the contact points, I'm going to get rid of that as well. So here we are in the draw function, and here's where we display the contact points. I'm just going to comment those out for now so they're not used. Okay, let's run this and let's get a baseline for our performance. So I'm going to add about 100 bodies here. Okay, so we have 100 bodies now randomly placed in our physics world. So to run the physics step is taking about 2.39, 2.4 milliseconds. And there's one at 2.35. So anywhere from about 2.35 to 2.4 milliseconds. Okay, so that's going to be our baseline. Let's close this out, and let's go ahead and implement the broad phase and the narrow phase. All right, so inside of our flat world, I'm going to scroll over here to our step function. So the broad phase is basically this double for loop. And what I'm going to do is I'm going to create two functions. I'm going to call one the broad phase and one the narrow phase. So I'm going to scroll right down here, right below our physics step function. Let's make a broad phase and a narrow phase. And I'm just going to cut this code out. So the double for loop is going to be our broad phase. And then this single for loop here at the end is going to be our narrow phase, where we actually resolve the collisions. And then inside of our physics step right here, let's go ahead and call the broad phase and then the narrow phase. And you can see this, to me, this cleans up the code quite a bit as well. So it actually looks cleaner, and it looks, we're actually spelling out the list of things that we're doing. So it's easier to read as well. Now the movement step, I want to put that in its own function as well. So I'm going to scroll down here and past the narrow phase function. Let's make another function. I'm going to call this step bodies. And I'm just going to take this movement code out of our step function. So here's the movement step. We loop through all the bodies and we move them. Let's cut that out and put it down in this function. Okay, and the step bodies function, we're going to need to provide the update time and then the total number of iterations. So we'll just pass those in as arguments to this function. So let's give it the time in seconds that have elapsed in this update, and then the total iterations. Okay, now we can scroll back up to our physics step. Let's call the step bodies function. Okay, and I'm going to get rid of some of these comments here. We don't need that comment. Now the contact list clear function, I'm going to move that up here to the top, but we're actually going to get rid of that list here very shortly. Okay, so here's our complete physics step now. Clearing the contact list, stepping the bodies, calling the broad phase, and then the narrow phase of the collision detection. Cleans up that code quite a bit. Now, in fact, I commented out the contact points list. I'm actually going to get rid of that code completely so it's not in there at all. So let me go through this flat world and let me get rid of all the contact points. Let me get rid of all the contact points commented code. And then back in our game class, here's where we're drawing the contact points. I'm going to get rid of that as well. And the code looks really good. So inside of our draw command in our game class, we are just drawing every entity. So that looks good right there. All right, so back in our flat world, let's continue to work on the narrow phase and the broad phase. So inside the broad phase, I don't actually want to do this collide function. So I'm going to cut this out of here completely. And then let's put it down in the narrow phase. So right here, I'm going to paste in the collide function. Oh, and then right here inside the narrow phase, this is the commented code that we were saving the contact points list. I'm going to get rid of that code as well. Okay, so that'll just make things easier to read. All right, so there's our narrow phase. Still needs some work, but we need to work on the broad phase first. So inside the broad phase, I want to actually save collision pairs. So what I'm going to do is make a list of collision or contact pairs. It's just going to be a list of pairs of integers that represent the index of these bodies in the body list. All right, so I'm going to scroll up to the top here. Instead of having a contact list where we save the contact manifolds, let's get rid of that list, and I'm going to make a contact pairs list. So we're going to call this contact pairs. So I'm going to save these contact pairs using something in C# called a tuple. Now, what we could do is I could create a struct up here, and I could call this contact pair. And inside this struct, we would have item 1 and item 2. So what I'd do is I'd actually make a list of contact pairs. So inside of our broad phase, we're looping through every body, comparing it to every other body, and we're determining if their axis line bounding boxes are intersecting. If they are, we want to save these contact pairs. So we'll just add these contact pairs to our contact pairs list. Something like that. But C# actually has something called tuples, and tuples allow us to save things in a really easy manner, or save a list of items in a really easy manner. And the way we do that is by opening a parenthesis, making a list of the things that we want to save, separated by commas, and then closing the parenthesis. In this case, we want to save 2 integers, and so we have integer 1 and integer 2 here, and we're going to save those as contact pairs. Inside of our flat world, instead of having a list of manifolds, we need to change this to be contact pairs. Inside of our step function, every time our function steps or iterates, we need to clear the contact pairs list. And inside of our broad phase, we're going to add the contact pairs. And the way we do that is by adding a new tuple. And we just pass in I and j, just like that. So by passing in index I and index j, we're saving the indices in our body list of 2 objects that are possibly colliding. All right, so that's the complete broad phase. And you can see the broad phase is very, very simple. We're just looping through every body, comparing it to every other body. We determine if their axis line bounding boxes intersect. And if they do, we're going to save the pair of indices that reference those bodies in the list. Okay, now in the narrow phase, instead of looping through the contact list, we want to loop through all the contact pairs. We're going to go ahead and get the indices of those contact pairs. This parentheses int is saying that this is going to be a tuple. I'm going to call it pair, and we're just going to retrieve it from the contact pairs list. Okay, now that we actually have the pair, let's go ahead and get the flat bodies that are associated with these indices inside our flat body list. So we're going to have flat body A and flat body B. So from the body list, we're going to get index number 1, which is pair item 1. And then body B is going to be item number 2. Okay, so inside of our narrow phase, we're looping through all the pairs. We get the actual pairs, and then we have the bodies associated with those pairs. So now we can pass these bodies into our collide function with body A, body B. We find out if they are colliding. We separate the bodies if they are. We find the contact points. Now, instead of saving the contact points to our contact list like we were doing before, I'm going to go ahead and get rid of this contact list. So we actually get the contact points. We save the manifold as a contact. We don't have to actually save it to this list down here, so I'm going to get rid of that. But we do need now to resolve the collision, so I'm going to move the resolve collision into this function here as well. Okay, and that should be it for the narrow phase. So now the narrow phase takes the contact pairs, it gets the bodies that are associated with those pairs, and so now in the narrow phase we determine if they're actually colliding. If they are, let's separate them, let's find the contact points, and then let's resolve the collision. That should be it for separating our narrow phase and our broad phase. If we look at our code, it's a lot easier to read now. Inside our sep function, we're iterating. We're clearing the contact pairs. We're stepping the bodies through their movement. We're finding contact pairs through the broad phase, and then the narrow phase, we're resolving those conflictions. All right, so let's run this now and see if we got any performance increase. So I'm just going to randomly place 100 flat bodies or boxes here. Okay, right at 100 there. And so at 100, our step time is anywhere from about 1.77 to 1.78. And at the highest, I'm seeing 1.85. So with this, the lowest is about 1.75. And then at the highest before, we were at 2.35. So if we do 2.35 milliseconds divided by 1.75, all right, so we've increased performance about 1.34 times. So actually pretty decent increase in performance there. All right, so that's it. We've separated the broad phase from the narrow phase. The code looks a lot cleaner. It's easier to read, and we got a performance improvement as well. So one last thing I'd like to talk about is kind of a roadmap here. We're getting to the point where our physics engine is almost complete. Now, when I say complete and a physics engine in general and adding features can go on for a long time. We could add a lot of features to this. And so if you're looking at a roadmap here, we're getting close to the point where we are complete with the goals that I had set. So in order to make this physics engine complete, what I'd like to do is implement rotation on the bodies and friction. So once we have those two things, we are going to call this physics engine complete. There are lots of things that we could add to our physics engine, and we could go on for a long time with this. But the purpose here is not to have a super complex physics engine, but to have a simple physics engine that allows us to learn how these things work and have a better understanding of physics in general. But for now, that's our narrow phase and our broad phase.